Hello everyone! Welcome back to my channel. Today we're diving into the world of object-oriented programming with Java. Object-oriented programming, or OOP, is a crucial paradigm in software development. It helps us model real-world entities in a structured and efficient way. Before we jump into coding, let's understand the core principles of OOP: encapsulation, inheritance, polymorphism, abstraction. Encapsulation keeps data safe and bundled within a class. Inheritance allows us to create new classes based on existing ones. Polymorphism enables flexibility, and abstraction simplifies complex systems. Now, let's bring these principles to life with the help of classes and objects. A class is like a blueprint, defining the structure and behavior of objects. Here, we have a simple car class in Java. It has attributes like make, model, and methods like startEngine and accelerate. Now, let's create instances of our car class and see how they interact. Meet our cars: Toyota Camry, Ford Mustang, and Honda Civic. As we start their engines, accelerate, and turn on headlights, notice how the car class structure helps us organize and reuse code efficiently. The benefits are clear: structural organization and code reusability. These principles make OOP a powerful tool for software developers. Let's dive into the code. Private variables, constructors, and methods play key roles. Private variables ensure data security, while constructors initialize objects. Methods like accelerate and break provide functionalities, promoting encapsulation and abstraction. Now, let's run the Java program and witness our cars in action. This simulation mirrors real-world scenarios, showcasing the power of OOP. To wrap up, we've explored the fundamentals of OOP using Java. The car class example demonstrates how OOP enhances code organization and reusability. Before we conclude, here are some additional tips for mastering OOP and Java. And if you found this video helpful, don't forget to like, share, and subscribe for more content. I'd love to hear your feedback and suggestions for future videos. Thanks for watching, and happy coding! Mastering encapsulation, best practices, and pitfalls. Let's dive into the world of encapsulation, a cornerstone of object-oriented programming. It's all about packaging data and methods into a single unit, a class, while hiding internal details and exposing only necessary interactions. Encapsulation bundles attributes and functions, providing control over data access. This boosts code security and maintenance. For instance, consider a person class with attributes like name, age, and address. These are private, only accessible via specific methods within the class. Let's look at a code example. We have a person class with private attributes, name, age, and address. The constructor initializes these when a person object is created. Getter methods such as getName, getAge, and getAddress let external code retrieve private attribute values. Setter methods like setName, setAge, and setAddress allow external code to modify these values. Can you guess what the celebrateBirthdayWas method does in our person class? That's right, it increments the person's age and prints a birthday message. The main method showcases how to interact with encapsulated objects. It demonstrates creating a person object, accessing attributes using getters, modifying attributes with setters, and invoking the celebrateBirthdayWas method. Best practices for encapsulation include keeping attributes private and providing meaningful getter and setter methods. Avoid excessive exposure of internal details, which can compromise data integrity. One common pitfall is overexposing internal details, leading to data integrity issues. Another is neglecting to provide meaningful getter and setter methods, limiting interaction with the class's internal state. Mastering encapsulation is key to effective object-oriented programming. It maintains data integrity and controls how external code interacts with a class's internal state. In summary, this code showcases the principles of encapsulation by encapsulating the attributes of the person class and providing controlled access to them through getter and setter methods. This helps in maintaining data integrity and controlling how external code interacts with the class's internal state. Practice with different code examples and interactive quizzes to reinforce your learning. Happy coding! Advanced inheritance techniques. Inheritance is a key concept in Java. It allows a new class to inherit properties and behaviors from an existing class, encouraging code reusability and class hierarchy. Let's start with a superclass animal. It has a private field name and a constructor that initializes this field. It also has a getName method to access the animal's name. Lastly, it has a makeSound method, which prints a generic sound. Now, let's create a subclass dog, extending the animal class. It has an additional private field breed, specific to dogs. The constructor takes both name and breed parameters, calling the superclass constructor to initialize the name field. The getBreed method allows access to the breed. The makeSound method is overridden to provide a specific sound for dogs. Lastly, it has a wagtail method, specific to the dog class. In the main class, inheritance example, we first create an instance of the animal class, generic animal. We call its methods to demonstrate the superclass functionality. Next, we create an instance of the dog class, myDog. We call both the inherited methods and the methods specific to the dog class, demonstrating the power of inheritance. Let's look at a code example. We initialize generic animal with generic animal and call its getName and makeSound methods. Then we initialize myDog with Buddy and Labrador, call its getName, getBreed, makeSound, and wagtail methods. Inheritance in Java allows us to create a hierarchy of classes, promoting code reusability. By understanding these advanced techniques, we can better design and implement our programs. Understanding polymorphism in Java. Polymorphism in Java allows objects to be treated as instances of their parent class, not their actual class. It represents different underlying types with a single interface. Java has two types of polymorphism: compile time and runtime. Let's start with the superclass shape. It has a method, calculateArea, that prints a generic message and returns 0.0. This is our base class. Next, we have the circle class, a subclass of shape. It has a private field, radius, and overrides the calculateArea method to calculate the area of a circle. This is an example of polymorphism. The rectangle class is another subclass of shape. It has private fields, length and width, and overrides the calculateArea method to calculate the area of a rectangle. This is another example of polymorphism. In the main class, polymorphism example, we create instances of both the circle and rectangle classes, but store them in variables of type shape. This demonstrates polymorphism, as we can treat objects of subclasses as objects of their superclass. The calculateArea method is called on both shapes, and the overridden versions in the subclasses are executed based on the actual type of the object. This shows runtime polymorphism. So, polymorphism in Java allows us to use a single interface to represent different underlying types. It's a powerful tool that makes our code more flexible and easier to maintain. Understanding abstraction in object-oriented programming. Abstraction is a key concept in object-oriented programming. It simplifies complex systems by breaking them into smaller, manageable parts. Abstraction hides unnecessary details and exposes only the essential features of an object. Let's illustrate this with a programming example. Consider an abstract class, shape. It contains an abstract method, calculateArea, that must be implemented by its subclasses. It also has a concrete method, display. Now, let's introduce an interface, colorable. It declares an abstract method, setColor, stringColor, that any class implementing this interface must implement. Next, we have a concrete class, circle. It extends the abstract class shape and implements the colorable interface. It provides an implementation for the calculateArea method and the setColor method. It also has a method specific to itself, displayInfo. In the main class, abstractionExample, we create an instance of the circle class. We set the color using the setColor method from the colorable interface. We call methods from both the abstract class and the concrete class. This demonstrates abstraction. We hide the implementation details and expose only the essential features. Abstraction makes our code cleaner, more flexible, and easier to maintain. It's a fundamental concept in object-oriented programming. And what is a constructor, and how does it differ from a regular method? Let's dive into the world of object-oriented programming, focusing on constructors and methods. A constructor is a special method used to initialize objects when they're created. It's automatically called when an object is instantiated. Constructors share the same name as the class and don't have a return type. They set initial values for object properties. Methods, on the other hand, are functions defined inside a class. They perform specific tasks and can return a value. There are two types of methods: instance methods and static methods. Instance methods are called on an object, while static methods belong to the class and can be called without creating an instance. Method overloading is a feature that allows a class to have multiple methods with the same name but different parameters. The compiler determines which method to call based on the number and types of arguments passed. Method overriding occurs when a subclass provides a specific implementation for a method already defined in its superclass. The overridden method in the subclass must have the same signature as the method in the superclass. So, how does a constructor differ from a regular method? The key difference lies in their purpose and behavior. A constructor is used for initializing an object, while a method is used for performing a task. A constructor is called automatically when an object is created, while a method needs to be explicitly called. In conclusion, constructors and methods are both crucial components of object-oriented programming. They each have their unique roles and functionalities, contributing to the flexibility and reusability of code. Understanding their differences is key to mastering object-oriented programming.